Bertrand has a broad interest in theoretical seismology, tomography, catalog creation, but also observational seismology. We've had the great pleasure to work with him in the field. He's a real wizard, and he's also recently started his own company, providing observational seismology services for a range of industry application using a mixture of sort of fancy modular hardware and instrument-based machine learning routines. So pretty exciting. So he's going to talk to us about a range of efforts that he's pursued over the years with focus on structure and seismicity in South America. And his title is Seismology at the Edge of the Andes, Insights and Challenges from Chile. Welcome, Bertrand.
Very much for the introduction. Yeah, so as Torsten explained, I'm going to present basically an overview, a fast overview of the last 8 years in Chile. The Chilean area and South America in general is very interesting for seismicity and for seismology because it's very, very, very active. And there is a lot to do, basically, because there is it's so big and so complicated to get everywhere and study and put stations and everything that it's a very cool, fun playground to go around and study seismicity. So as a start, basically showing this diagram is the idea of what we can see. Thank you. As seismicity in South America, it's a basic drawing of what we know today to be the seismology of a subduction zone with big earthquakes, mega earthquakes that we have a few in. Thank you. In South America, tsunami earthquakes, tremors, earthquakes, slow earthquakes with no seismicity, shallow ones, deep ones, intraplate, intraplate, interplate, double zone seismicity, also surface seismicity that's linked as well. This is a diagram of everything we can see, and the cool thing in Chile and South America is you have all of that, but in Chile you have all of that at a relatively short time scale. So we can observe all of that within 100 years, you have everything basically happening. This is a work we did a few months ago about the Latin American seismicity, and this is basically what I just showed you, but in with real data. So you have Mexico, Central America again, and Northern South America, and finally Southern South America. A lot of seismicity, very big earthquakes, basically everywhere. The giant earthquakes mostly in Chile. We have like information and data about very large earthquake more than 5,000 years ago, but also more recent one and the biggest one ever recorded with modern seismicity in 1960 in southern Chile. That's for the mega earthquakes, more than 1,000 kilometers of fault zone, but also smaller events, big events still, but smaller events. One big one for Chile was 2010, magnitude 8.8 in the Maule earthquake. The earthquake didn't break many things. Basically, one building went down. But the tsunami following the earthquake and the way the authorities managed the situation was very critical. Many people died. And that really remotivated the observation of seismicity and earthquakes in Chile in particular. Very interestingly, we can see all of the type of the earthquakes in South America, the shallow ones, the deep ones, so mostly in very deep ones in northern Southern America. But we also have that in Chile, a lot of slow slip events, either shallow or deep, and a lot of seismicity everywhere. Regarding Chile in particular, So in this figure, what I'm showing is basically the catalog of the National Seismic Network, the recording. And what we can see is basically we have a lot of activity in the north, in central Chile, a bit less in this area here, but we are going to see why, and almost no activity to the south. This is not the reality of what's seismic or of the Chilean seismicity, but this is the observation we have from the national network. Just a reminder, this is from 18 degrees south to 43, 44 degrees. So the range is very big. Chile is going to 50 something, so it's more than 4,000 kilometers from north to south. There is a lot of area to cover and to study. The way the seismology, the seismicity is monitored in Chile is done through the CSN, the Centro Sismológico Nacional, National Seismic Center of Chile. This is based in the University of Chile. I worked there for 2 years. The responsibility of the CSN is to monitor all the seismicity, but oriented to the risk, and the risk is the tsunami in Chile. The Chileans actually know how to build paraseismic. They build paraseismic very well. It's actually something that was acquired many years ago. When the Spanish arrived to Chile, very interestingly, they made the local build churches and everything, and they built churches the way they knew how, and they made them paraseismic. They knew how to do that many years ago. So it's very interesting. Nowadays, the CSN is doing the monitoring. So the CSN appeared in 2012. There was a response to the very big earthquakes of 2010. Before that, the SSN, the service instead of the center, was operating. That was created in 1906 by a French guy who was invited to Chile to create the service. So French people are very good for seismology. Thank you very much. Nowadays, the network counts about 100 stations. This is a map of the stations since the 80s. So some sites have been unequipped, some others appeared, but not all of the network is operating. A lot of stations in this area. This is Santiago de Chile. 1/3 of the population of Chile lives actually here. This is why you have so many stations. Northern Chile is also very well covered. This is the IPOC zone. So the network from the north is actually a consortium between French and German, mostly German, to be honest, who build a network to study northern Chile. The rest is basically the CSN. Some stations now come from the OFDAS, which is the volcano observatory, and a few stations from Argentina and from Peru has been also shared and are used to monitor the seismicity in Chile. So this is the state of the observation. So a while back, we wanted to have a deeper understanding of the network, what we have in the catalogs of the CSN and what kind of seismicity we were observing. And so we started studying the catalog by looking at the stations and what station existed through time and which kind of records we had. So I'm going to focus the next few slides on that. First about the stations. So these two maps are before 2012 and after 2012. This is the network. The colors and the shapes give you the kind of instruments we are recording. Very interestingly, from the 80s, what we basically had was monitoring in the central area. This is Santiago, as I said. 1/3 of the population lives in Santiago, so that was the main goal and the main operation center, basically. One of the reasons they didn't go north and south is because it was far away, so it's costly, obviously, but also for data transmission. There is no real-time transmission in these times in northern Chile, southern Chile, so there was no way to really register seismicity outside of Santiago. After 2010, most instruments became broadband stations. The entire country was covered with a new network. What happened at the CSN creation in 2012 is that the government put a lot of money and energy in building a real network. And so since 2015, the network is basically installed for the entire Chile. How does that translate in the catalog? Well, basically, we are looking at the same thing before 2012, after 2012. And this is the repartition latitude of the seismicity of the catalog. So many things very interesting here. As I said, from the 80s, most of the seismicity we observe are located in the central area of Chile. This is because we had no station outside of Santiago. There is a gap here. That's an engineer that was fired just after. So, you know, it's not really third world country, but still in development. We basically had no backup of data. And the first backup of raw data of like the traces and everything started just there. Buying servers, installing servers in a smart way, so outside of Santiago in a remote place and everything is not that simple in Chile to operate. Justifying the cost of that, finding a place to install and everything, it's complicated. So yeah, the backup server is running since 2022, more or less. But yeah, it's a complicated thing to do. Another thing is you don't see here is that before 2011, we have no record, no real time. I mean, the traces basically disappeared. Everything disappeared in 2011. Someone was fixing the air conditioning in the server room, and he didn't know how to plug his equipment, so he unplugged a server basically. And the disks basically burnt and we lost everything. So there is no real time, I mean, the waveform, there is no waveform before 2011. And this company who fixed the AC never was hired again to fix anything in the university. But this is a problem with backup. So now all the waveforms are saved in Earthscope. So hoping that Earthscope still works for the next few years. Yeah, very interestingly, we have very few seismicity in this area. The north of Chile is very active. The central zone is very active. You have less seismicity here, less seismicity here. But if we go back, it's also a place where we have less stations. This is 1 degree, so 100 kilometers between stations, we have less seismicity.
But some of these clusters are real, right?
Yeah, most of the clusters we see here are actual clusters. There is a lot of clusters in all Chile. We can see like lighter line here and here. These are earthquakes, the Maule earthquakes here. You have one here, you have one here. 2007 here, you have one. But also you have like this very clear line is a cluster. You have many, many of them. So still exploring the catalog and exploring the data. One thing we did was looking here at the number of stations used to locate the earthquakes. And very interestingly, it changed a lot in time. So if we look at the past, we had very few stations. So a few stations per earthquake seems normal. Then a bit more stations start to appear to register every earthquakes. And then in 2010, magnitude 8 earthquake in the south, 8.8 in the south, way less station per earthquake. Basically, they had so much seismicity at the beginning, they started to pick a few stations, 3, 4, and pass to the next earthquake, but that lasted for 4 years. So that's, instead of being just a decision taken at the start of the crisis, it's a political decision that lasted the entire time until 2004, and then they started to use more stations again to process the data. So it's very interesting to see this figure, I think, because what we see is the catalog is not only a representation of the seismicity, it's also some kind of politic of the way of doing things in the seismic center, and you have like inconsistency in quality and time. About magnitudes and number of events per year. So this is the number of events per day. So right now we are about 30 events per day. In terms of magnitude, we used to have CODA magnitudes up to 2002. Thank you. They switched to local magnitudes after that and have a few W phase events, magnitudes for the largest events. And now they use the W phase magnitude since 2016 to determine magnitudes for the biggest events. This is the same view, magnitudes for every zone. So northern Chile, northern central Chile, central Chile, and southern Chile. So you have very interesting things. First, the switch between CODA and local magnitude give you some kind of weird connection here. This is a temporary experiment when they try to lower the magnitude, the minimum detection magnitude they could process. So the processing is basically magnitude 3 and above. This is a contract they have with the state. They have to locate and determine the magnitude for every magnitude 3 and above. They try to limit up the threshold at 2.8 to be sure they have everything. But they can detect lower magnitudes, and this is what they do sometimes. So the threshold is going up and down. Very interestingly, when you have the very big earthquake in Maule in the south, you have no seismicity in the north. The stations are there, but they just didn't process the data because they were concentrated. All the energy was in the south. So it's very interesting to have a look at the catalog and not overinterpret these kind of things because you have huge gap in the data just because you have so much work in the south. You also have some temporary experiments with many stations in the same place that can appear in the catalog. So the catalog is not like a uniform catalog of data you have. It's very complicated thing with, it's a bit alive, you know, in a sense. You have a mix of everything. That's really interesting. Anyway, this catalog is huge. You have a bit more than 100 stations, about 30 events a day for recent years, at least. All seismicity of magnitude 2.8 and above, and data since the 80s. So in the 80s, less data, mostly in the central region, but a lot of earthquakes still. The catalog from 82 is more than 130,000 events. So that was a great opportunity to do tomography. The goal here was, the idea was to enhance the location process. The CSN uses some kind of 1D flat Earth models to locate earthquake in a 5,000 kilometer country, so it's a big problem. The velocity model for a subduction zone is really not flat, really not simple geometry, so doing a tomography makes much sense to enhance a bit the location and all the process. So this is what we did. If we look at temporary networks and temporary studies, maybe some of you have done that at some point, or some of you will do that at some point. I gathered about 40 different experiments, temporary experiments in Chile. The very interesting thing is it represents 900 station sites. So that's a total of 1,000 measure points in the entire Chile. Temporary experiments usually run for a few months to a few years. There is so much seismicity, you can detect in northern Chile up to 400 earthquakes per day. If you look at microseismicity and everything, so installing a station for 1 month, you have like plenty of earthquake to process. The very interesting thing is you have very low magnitude local events using these networks. The problem is in some area you have no stations, no experiments. Basically, this area is very interesting, I think. Nowadays, since a few years ago, we have more experiments here, and effectively there is a lot to see. But the thing is, no one lives here. So no station, no seismicity, no problem. Once you put stations, it becomes interesting, and you start finding like slow slip earthquakes, and you start finding, and everyone and all the experiments then start working there because there is like stuff to find in this area. So this is 2024, more or less. We have like studies in this area, but before that, nothing. Maoli earthquake also brought some OBSs in Chile, so that was very fun to have data in the sea and a few experiments in this area. This is the flat slab of Chile. I'm not sure we're going to see figures, but there is interesting stuff that was done in the 90s here in this area. So using both the CSM data plus the temporary experiments, that brought about 100,000 more events. I got this huge catalog, so we don't see like 200,000 events here, but there is about 250,000 events in this map. It's a huge catalog with more than 2.5 billion millions of P waves, a bit less than 2 million S waves readings, about 1,000 stations. But the problem is the disparity of the catalog. You have like all qualities mixed up. And of course, when you get to a certain size at a point, you have problems in your catalog. You have errors, you have all of that. So the cleaning, the merging and cleaning was a complicated phase to process. One of the approach, and I'm talking about that because it's very efficient, and we developed a method around that, and it's very efficient. It's using a validity diagram, validity-like diagram approach. Basically, we are comparing for the same event, P waves between two stations versus S waves of the same stations. And for every pair of stations that have both P and S wave, we do a dot on the figure. So if you do the math, you can see that the difference gives you the VPBS ratio. So this is this line, basically. Everything outside of the line is probably a picking error. In Chile, because you have the slab, you have a lot of errors, picking errors, recognizing the refracted waves in the slab as the first arrival or the direct wave as the first arrival. That's the kind of confusion. And every other errors that the picker does. If you have picked earthquakes once in your life, you know that's the kind of errors that can arrive. So this is a very efficient way to clean up the catalog. And we worked a lot on that. The other thing was to look at data quality. So based on that, and based on the dispersion of basically looking at the dispersion of this curve, we can also, per catalog, we can also discriminate good quality catalogs and low quality catalogs and give some of sense of that on the data quality we use for the different earthquakes. To make the tomography, so the idea is to have a very, very high quality, but also a very, very big model. So the way to do that was to cut Chile in 6 pieces. These 6 boxes became the 6 tomographies we realized. Taking this approach is basically having 6 models of 800 kilometers from north to south, so at 8 degrees each. East to west is between 200 and 700 kilometers. But getting this approach gave us the possibility of doing a meshing of 6 kilometers horizontally and 3 kilometers vertically. So we can cover all Chile with a reasonably low resolution, high resolution for the model. And using both P waves and S wave, we recovered VP and VPBS ratio. That gives us VP and VS models, of course. I don't know if you're very familiar with tomography. Very basically arrival time. So we don't use P waves and S waves. We use P waves and the difference between S and P. The idea here is to avoid the T0 problem. Many experiments and temporary experiments in northern Chile, especially the old ones, don't have a good clock. So we know that the times are probably wrong, but we know that the time differences are always right. So this is a good way to avoid this problem. What we did was compute for VP and VPVS ratio, but also it's a joint inversion for location of earthquakes. And also one parameter I didn't put here is site effect. So it's not the real site effect as we understand in science. It's more like a station site effect that really depends on what's happening below the station. But the result is not very relevant, so I didn't put it here. It's just mostly to stabilize the inversion. Well, the theory, I'm not going to enter into details, but basically the arrival time is the origin time plus the propagation, and the propagation you compute at the integral of the slowness along the ray. That's for P wave arrivals, and for the differences, you don't have the T0, you just have the integration of both rays, P waves and S waves. The interesting thing we do, this is the code we developed during my PhD with Bertrand Potin, who is the co-author of the Tarantula and Ballet 1982, which is the base for the inversion in geophysics, is that we use a regularization that gives us the possibility to not depend on the grid. And this is very interesting because if you look at the classical SimulPS or classical codes for tomography, they use a very grid-dependent inversion. Every cell is determined by the rays that passes through the cell. And so if you change the grid, you change the model. And this is a big problem because you need to have big cells to have a lot of rays inside them. And you are very dependent of the size of your grid. And the model is dependent on the size of the grid. The way we do regularization, sorry, big word, is by using the covariance on the model. So basically, instead of having direct relation between rays and cells, we have a function that gives us the influence of each ray on every cell of the model. So of course, the influence is basically controlled by the rays that are very close from the cell you are determining. But it's a good way to not have a correlation between the grid and the results. It lets you basically compute the model everywhere with more or less precision, depending on the number of rays going by close to your cell. But it's a very nice way to do the job. One big problem is to compute the inversion of a covariance matrix, and this is why people don't usually do that, because you have this huge matrix with millions of parameters and you have to invert it. And it's very complicated. Thankfully, if you choose a good kernel, good correlation kernel, you can actually compute the inverse, the square root of the inverse directly. You don't actually need to do the inversion. You can compute it and determine it analytically. So this makes the computation very reasonable, and you can compute the inversion very fast. Within an hour, you have one iteration, and you need about 25 iterations to get an entire model with millions of parameters. For the resolution, we use a quasi-Newton algorithm. We solve that using the NSQR code. And the big problem is we have so many data, we cannot control the quality of every data. So instead of trying to have the perfect catalog and the perfect data, we use a lot of systems and filters basically to tolerate errors on the data. So for example, for the PDF, we don't use Gaussian math. We use something that's lets data be more wrong or problematic. We have filters for outliers. We use criteria to converge and have a better model for conversion and other stuff. Many stuff are programmed. The very big motivation for this code was to do inversion in Chile, in South America, not necessarily in Chile, but in Ecuador, in Peru. And the idea is that you have a very heterogeneous catalogs where you don't control everything. And often in these places, people don't remember the choices that were made like 10 or 20 years ago. And so you lost the information of why the quality is this way, why the quality is that way. And so the idea is having a very strong code that it's able and capable of managing all of that is very important. So yeah, once we did the 6 tomographies, we basically joined all the models, and we got this huge model for the entire country regarding ray path. So this figure is just to give you a sense of the quantity of data per cell. So remember, the cells are 6 kilometers horizontally and 3 kilometers vertically. The colors give you the length of ray per cell. Blue is very short, less than 1 kilometer per cell. Yellow is more than 10,000 kilometers per cell. A and A, this is at the coastline. The B1 are 50 kilometers inside, and the C1 is 100 kilometers inside on land. So you have north, central Chile again, southern Chile, from 18 to 32 and 32 to 46 degrees. So in the south, we have very few data, very few earthquakes, so not a lot of resolution. In the north and in central Chile, we have a lot of rays, a lot of seismicity. In some areas, we have so many rays, we get more than 10,000 kilometers of ray path per cell, per 6 per 3 kilometers cells. So it's very interesting, and you have a lot of information. So I'm not going to show the tomography yet because it's so big. But one of the things I did based on this tomography was to build a slab topography. Using both the velocity model, both P-wave, BPBS, and VS, and the seismicity relocated in the model, we were able to build a topography of a slab. So the problem is when you build this kind of topography, you take choices, you don't know if the quality is going to be the same everywhere, and you don't really see what you do. So the way we worked was we did a series of cross sections in the models, and we went picking basically what we were seeing. We did that for P waves in the entire country. We did that for S waves, for BPBS ratio, for the seismicity, several passes in the entire country. And we looked at the topography we built, basically joining all of these data points and seeing if it was coherent or if we were having problems. So every small dot you see in this figure is a dot we did manually picking the depth of the slab. Outside, this is the slab 2.0 model. So what we did is basically an interpolation between the data we had and the slab 2.0 to have some kind of continuity. Very interestingly, can you move the...
Yeah.
Just where the information. Good. So interestingly, we can see that there is a lot of difference, up to almost 40 kilometers difference at depth with the slab 2.0 model, which is a bit problematic. We're not expecting that. But then when you read the paper about the slab 2.0, you understand very fast that the data they use in this part of the world is basically up to 50 kilometers at depth. So this is the coastline of Chile. The slab is about 50 kilometers. And then they connect with deep tomography, mantle tomography at 600 kilometers at depth. So they have a few data here, a deep slab up there. They have to connect, and basically the angle is wrong. If the angle is wrong, then the more east you go, the bigger the error is. And this is what we see. Very interestingly, something that doesn't show much a bit, but just a little bit, is there is some kind of oscillation we see in the north here. So it's moved out, but it's something I saw basically picking the slab in the north, and a colleague of mine using completely other methodology in Mexico is seeing basically the same thing, some kind of 50 kilometer long wavelength oscillation in the slab. So this is interesting. We didn't look much into it, but there is something to understand with this small oscillation we see in the north. Other interesting thing is this. So this is controlled by very few points here. So it's we don't have much control, But in this area, we have a very interesting structure in the seismicity. I'm not going to talk much more about it because we didn't study it yet, but I have to convince now Torstein to give us more station to study the seismicity just there. He doesn't know about it yet, so don't say anything. But yeah, this is what I'd like to be the next year project.
Sounds good.
Yeah, cool. So about resolution, once we looked at the model, the first thing, so I showed the velocity model to Emily Brodsky when she came to Chile, and the first thing she told me was, no, but what's the resolution? What you see is noise. So, okay, let's see if it's noise. So this is basically checkerboard. So what we are seeing here is not a flat map, it's actually the velocity field on the slab surface I just showed you before. We took the model, we interpolated on the slab, and we are looking at the resolution we get on the slab surface. So these are 50-kilometer cells. It's very coherent with the map of the rays I showed you before. Good resolution in the north, good resolution in the central Chile, no seismicity in the south, so yeah, it's expected. Lower resolution in the Norte Chico, small north, where there is no station for many years and so not a lot of data. If we look at smaller cells, this is 20 kilometers, we still have good resolution in the north. We lose basically all the information in Norte Chico, and central Chile is well resolved again. So this is very interesting. And now finally, some velocity models. So you have S-wave differences. Blue is faster than expected and red is slower than expected. VP and VPBS. So first thing is we have these very slow area here. This is the OBSs we have from the Maole experiment. A lot of sediments in this area, so slow velocities are what's expected. We have a bit the same in the north. But very interestingly, what we can see is we have all these structures on the slab. So you have fault zone, you have seamounts, ridges, many things in the south. This is a triple point, a bit south, but you have the fracture zones associated to that. And we can see a relation between the seamounts and the velocity model at the coast, at least or close to the coast. So these results are yet to be published. I'm very, very slow at writing. So we are not there yet, but there is a lot of information there. And thank you, very good. There is a lot of information here, and what we see is coherence with many structures that people have seen in the looking maps of the thrust, and also we can relate many structures to the size of the earthquakes, the big historical earthquakes. If we compare the map with where the earthquakes happen and where the seismicity is, very interestingly, we can see that all these structures we can see here in the tomography correspond to hard limits for the earthquakes and the past earthquakes.
So when you do this, do you define a slab surface, or do you?
This is the slab
You pick that?
Yeah.
And then this layer would be what? How?
We interpolate the velocity model on the slab surface.
Okay.
So at every point of the map, I take the velocity model around the point. I have it's a small area. It's like 5 kilometers around. I do a mean velocity at each point. And what we see is the velocity at depth. The thing is, if I put the real velocity, because the depth is changing, you see the change related to depth and not really the change north-south or east-west. So what we do is we have the initial model, which is smooth, and we compare the velocity model we get with the smooth input model we have. So
and the slab depth you infer from a tomographically determined velocity.
Yeah. from the velocity model and the seismicity, I build the slab surface and I look at the velocity at the slab surface.
So the seismicity does put in the surface, right? Because tomographically, you have a smooth area.
Yeah, I mean, it's a mix of both, basically, because you see very well the slab in the VPVS, at least at shallow depth. Then you have the transition, you see the transition between interplate and intraplate seismicity. So you start picking at the seismicity and then just above, the seismicity. So you maybe have like a 10 kilometers error every point, but the idea is I picked in every direction. So you have like several readings for every point. And you get this map.
So those low velocities that you pointed out by the Malawi intersection, does that mean that's low velocity sediments that are not part of the slab? So they're subducting sediments?
There is probably a depth error, especially here because we are offshore. But it's also this anomaly is controlled by the OBSs we have here. We don't have OBSs anywhere else. So you have this anomaly is probably exaggerated a tiny bit. And the thing is, you don't constrain the depth of the anomaly is smooth. In the tomography, you don't have like hard limits, like velocity jumps, for example. So if you have a very slow area, it tends to get a bit elongated. So it's probably sediments above that, but the anomaly is extended vertically because we can't constrain it.
So some of that may be from accreted sediments.
I can't say if it's subducting or if it's like above sediments. It's very subducting a bit, but this anomaly comes from a very specific. If we had OBSs all along, we could like tune the model, but we can't do that because we only have OBSs here. So there are many things to interpret, and but this is the Maole earthquake area basically, and we know that there is sediment subducting, so it's coherent, the observation. Now, if we don't have this information, I cannot guarantee that it's 100% from the subduction. It's probably a bit extended from the surface as well. Yeah.
Could you help me point where is that's called Atacama?
Atacama.
Where is it on this map?
The slow sleep of Atacama. This is Copiapó. Copiapó is around 27. It's around here. This is La Serena. Vallenar is here. Copiapó is around here. So the slow sleep is here. The map I showed you with the slow sleep before, that was from last year. And we have like three new ones in this area now. So there are more data to look at in this area. So yeah, many things to see in these maps. It's interesting. Moving on, next topic, automatic picking. It's going to be short. So this is a resume of the experiments we did since 2019, since I arrived at the DGF. And the problem is we have way too many experiments. So it's very fun. I do a lot of field work, meet with a lot of animals and stuff, but we have way too much data. Remember what I told you, you can have up to 400 earthquakes per day per station. And this is all of what we did in the past few years. So first, Copiapó experiment, we had 10 stations we installed, 4 months in one setting and 4 months in another setting to have a very clear view of this area. These data are open, it's network 2V. They are open now in Earthscope. The Coquimbo experiment was really fun in this area. The idea here, for Copiapó was to look at the impact of the Copiapó Ridge subducting here. In Coquimbo experiment, it's basically the same. We have a fracture zone subducting here, and we wanted to see what's going on. The Tongo experiment, Puerto Aldea, it's a fault. So we had like 10 stations in a very small area of 50 kilometers by 20 kilometers. near the coast. It's a very interesting fault zone that we wanted to study. Then we did an experiment in the Kokuro fault, which is a superficial fault close to Santiago. Santiago is just there, so Kokuro is just up north. This is very interesting because these faults are not seen by the CSN, by the national network, because the seismicity is very small, but they are very dangerous because the extension of these faults in Santiago is the San Ramon fault. Historically, geologists can show magnitude 6 to 7 happening on this fault every few hundred years, and the San Ramon fault crosses Santiago. So it's potentially very dangerous, and the Pocoro fault is easier to study. It's the northern extension, but no one lives there, so it's easier to study. Right now, we deployed the green station here, which are in front of the DAS cable from Diamrivé. If you heard of the DAS experiment in Chile, it's DAS acquisition on submarine cables, and we completed the network with on-land stations. And as of yesterday, we installed this network. So the team installed this network in Santiago, studying another fault, another superficial fault, about 15 kilometers inside the Andes, but very close to Santiago again. And finally, best for last, Torsten stations installed in northern Chile, this very, very beautiful straight line of stations. So the idea is 2 networks within one. One is the straight line going from the sea to the Andes for receiver function study, and the other one is this network to better constrain the deep seismicity, 200, 300 kilometers of depth. The problem in Chile is, so Chile is completely wrong. It's way too thin to work in 3D, but the other problem is that because of the Andes and because of the difficulty to work at high altitudes, most stations are actually within the first half of the country, so everything is wrong. So the idea here is to complete the network with high altitude stations to have a better understanding of everything that we can. And this is running up to the end of the year, basically. So I've been working at the seismic network of the Alps when I was doing my PhD and my master degree. I came to Chile, I picked a few events, and after, when you've picked like 10,000 events, you get sick of it. And when the pandemic arrived, nothing to do, let's learn something new and let's do some automatic picking. Basically, that was the whole motivation of this project. That was just before the Greg Berosa group published the FaceNet. So I was doing like very new work, you know, like very exciting work, artificial intelligence. Then I lost the race to Greg Berosa, of course. But this is the problem in Chile. This is 4 hours. It's not a very good selection of window. It's just a random 4 hours of seismicity in Coquimbo. And within this window, we have 47 detected events, out of which 34 we can locate. We have enough data to locate 34 of these events. And this is a very random window. This is basically anything. So way too much seismicity in Chile, and automatic picking is absolutely necessary. So the way we do it is a bit different than what other groups are doing. The goal here is to detect small seismicity and micro seismicity. So we developed this software we call AI Picker because we didn't find a better name yet. So if you have ideas, submit them. The problem is 3 things. First, we have to detect. Then we have detect means detecting an arrival and also identify it as a P wave, an S wave, or anything else. A truck passing by or an animal hitting a cable or whatever. That's the first work, and this is the first software that does the detection. The second part is when we detect a P wave on an S wave, we train the pickers. The pickers just do the picking. And the idea here is to, at the same time, estimate the arrival time and estimate the certainty of the peak we are processing. So what we do basically is, instead of applying the software once on the track, on the waveform, sorry. We apply it many, many times. You have the arrival around this, and so basically we are going to move around in a sliding window, and we will do several peaks, and we can get mean value for the arrival time or median value for the arrival time. But the dispersion of the peaks gives us a good estimate of the uncertainty. And this is what we do, and it works well for microseismicity. And then the last part is gathering the peaks by earthquake. This is what I started calling the sorter because it sorts data. People call it odd names. And then finally get the catalog. So this is the entire process. And this is what we program. A few examples. So here you have the peaks for P waves with the orange ones give you the uncertainty window. So I'm very happy about these kind of peaks. Same for S wave. The uncertainty here is a bit exaggerated, but basically it works pretty well. These are 3 examples. I didn't cherry pick. It's just 3 earthquakes. And for an entire event, works pretty well. All the traces here. So this is the Coquimbo experiment again. Different type of stations, different type of sampling. Or not all the stations are the same instruments, not the same sampling rate, but it works pretty well. And in this example, we have all the peaks done by the automatic picker. So this is just one example, but it's pretty fun to look at. Other examples, this is 15 days in northern Chile. So the interest of using automatic picking is basically this, the same 15 days. The CSN has a few tens of events, we have a few hundreds. And this takes about 1 hour to compute. This is, well, it's manual picking, so it takes forever, but they do it in real time, so it's easier. One of the things was to differentiate ourselves from other software. So FaceNet is very good to produce very big catalogs, but what we wanted to look at was the microseismicity. Here is a comparison we did a while back in a poster where we compare FaceNet to the picker, and what we look at here is the detection rate for versus the signal to noise ratio. So we look at the signal to noise, basically the amplitude of the arrival. We compare it to the amplitude of the noise just before it, and we give basically the reading of how many good peaks we have with automatic method compared to manually picking everything. So we took 1 day of data, we picked everything manually. 4 people did the full picking for the entire day. So we had 4 people looking at the same faces to build a very complete catalog for that day, and we processed the data, and this is the result. So the very interesting thing is, for very low signal to noise, up to almost 5, our software does better than FaceNet, and then FaceNet does better for bigger events. Since we focus on microseismicity, this is the most interesting thing for us. And the other thing is, that doesn't show here, is that we actually detect way more events because you have way more small events than big ones. So it's very interesting. We get a lot of very small things correctly, both for P waves and for S waves. So this is very interesting. This is another example. The idea was to look if we can work on every kind of frequencies, and we did a test on these data. This is an experiment in Switzerland. It's a mining experiment where the research team basically did a data acquisition at 200,000 hertz within a mine, and they do fracking. So they inject water and they look at what they can detect. It's a very interesting study from Anne Obermann, who was published last year. And the cool thing is they have data at 200,000 hertz. So it's like something you don't get every day. So she gave me about 10 seconds of data. This is like 40 giga. But the very interesting thing is that if you look at local or regional events on a 100 hertz station, or if you look at a micro earthquake at 200,000 hertz, you have basically the same signal. It's basically the same thing. It's just the scale, the time scale changes. So we applied our software without doing anything, and we tried to look if we could detect and peak microseismicity. So this is the signal we got. A lot of noise, the noise from the operation, and here you have an earthquake. These are arrival from an earthquake you see on some sensors. We had to retrain a bit the software to be able to do the difference between doses, the noise, and the arrival. And this is the result we got. So this is a small retraining on 10 seconds of data at 200,000 hertz. We can identify the pulse from the operation, but also the P wave and S wave very well. So this is very efficient to compute and detect small microseismicity at any scale. But interestingly here, we took the model we trained on regional data at 100 hertz. We just gave it a few more examples of these kind of data to learn how to do that. And basically it works. It's the same thing. Just change the frequency and you get another kind of seismicity. And so, yeah. Finally, last part, and I'm finishing, it's just 2 slides, so I'm sorry for the time. This is another project I'm in. Basically, right now at the university, I'm working only half time. And the rest of my time is dedicated to a startup I created a few years ago. Created it with Javier Reyes, who is the commercial engineer. This is a career in Chile. You can be an engineer in commercial stuff. And was talking about like monitoring in mining and how the monitoring seismicity in real time for mines could be very efficient and very useful. And they are actually doing that, but they have a lot of trouble to apply it. So the idea I had was, let's do that. Let's apply that to mining industry and do real time monitoring for them. And so as Javier is really oriented to this kind of thing, he said, yeah, let's make a startup and let's build something. And so we started to do that. So the idea was to use the software I just showed you and implement it for real-time monitoring. So for underground mines, they usually have some kind of network. And so you can use the network they have, connect the software and do monitoring. So this is what we developed. But for open pit mine, which represents 80% of the mining industry in Chile, they don't have a seismic network. So you have to come up with something to get them to do seismic monitoring. And this is what we are doing right now. So this is a model of what we are building right now. This is a seismic station. The real thing is going to be bigger. Of course, it's about 70 millimeters from tip to tip. And the idea was, after installing 100 stations in Chile, I wanted to do something that actually requires zero work. So the station is here. The idea to install that is a button underneath it, you put it on the ground and it starts working. One cool thing about it is that we put the picker and the software for detection and picking within the station. So the station does the picking directly on the ground, transmits only the peaks and don't transmit the real-time waveform that lets us work at several thousands of hertz. We don't care because we don't have to transmit the data in real time. And yeah, this is basically the exciting part of what we are doing right now. So we are doing a prototype right now in part in China, part in Chile. And this is a project for like the end of the year, probably next year, we should have a few new kind of seismic station that does everything. So it's a very fun side project for me. I own way more debt than money right now. The idea of the software is basically the software I showed you. I developed that between the startup and the university with different applications. It's different. It's basically 4 modules: detector, picker, the sorter, and the database that you can connect between them. But the cool thing is you can install every module either in the station or in a server. You can connect servers together. It's really flexible and very easy to use. You can use data from the seismic station or from any system. Basically, C-Link works well. Other system, we have to develop the interface, but it's working fine. We fill up a database. We can get a catalog. We have a web interface. I can show you right now because it's not connected, but we can visualize data in real time. It takes about 5 seconds in mining industry. But at the scale of the mine, it takes about 5 seconds to get the data processed and get an earthquake, a dot on the map with magnitude and everything. And this is what we are doing right now. So pretty fun stuff. I hope it will get somewhere, some point. But the work is pretty fun. Thank you very much.
If you want to stick around, we're coming up for some questions.
Well, I have a quick question about the seismometer. What's the cost?
The prototype.
Have your final estimation of the market price?
The price it cost me, or the price I'm going to sell to you?
If you are going to sell, yes, because I'm
No idea right now.
Ballpark?
The thing is, the thing we are doing is we make it very flexible, and you can put basically any geophone within. So you can have small cheap ones, you can have bigger ones. The part we designed for the installation of the geophone gives you a range in diameter and length, basically, of what you can install. So, and the geophone is what will make the price of the station vary the most. Geophones cost between $30 to $600 for 2 hertz, 1,500 for 1 hertz. So it's basically what will control the cost.
But the size of the geophone is different.
Yeah, but we can adapt. We adapt to different sizes. That's the.
So you will change the whole size of the system to.
No, we have a range of things we can adapt. And
you measure that it can go down 1 hertz.
yeah.
Okay.
Depending on the brand of the you can find like small 1 hertz, so that works. Yeah. So no, I can't tell you the price. The thing is, I'm learning so much about like plastics and how to do like vacuum injection of plastics and things like that. So it's very like it's a new word for me.
3,000
What's 3,000?
thing with a decent geophone setup.
It's gonna be way more expensive.
Way more?
I mean, to you, yeah, you have money.
So it is funding resource depending.
Well, it really depends on who is buying. It depends on the quantity, basically. So when you do like the pre-series, you do like a silicon mold for the mold. Yeah. That cost the mold cost about $3,000. A bit more than actually, and the mold gives you 11 units. So you have to do the 11 units to optimize the price because the mold doesn't survive more than 7 days. So you have to do the 11 at once. If you want to do way more units, you make a metallic mold, but that costs about $30,000 to make. And then you can produce like a few thousand units. So it really depends on how many you are going to buy right now. Because it's it's completely, I mean, I have no idea. If you buy like 1,000, yeah.
Well, first the mining company is gonna.
Yeah. That's the idea.
Any other questions?
I have a couple of questions.
Yeah.
You mentioned that for your tomography data, you only use the Baghdadi approach for cleaning up the data. Did you ever use any other approach like signal to noise ratio or anything else like that? Is that the only thing you use, the Baghdadi?
So as I mentioned, for the CSN data, you have no waveforms before 2011 because they lost everything. So I can't use signal to noise ratio. I mentioned the validity because it's very efficient.
Yeah.
But other methods like basically locating earthquakes and seeing if you can adjust the data is very efficient.
Yeah, but that will help you to understanding your S and P pixels, they are put together. More or less, it won't give you an estimate of, if you can use the quality of the data, like the waveform data, and you don't have it, as you said.
No.
But, you can use the signal to noise ratio for weighting factors, things like that.
So what I use for weighting factors are actually the reading of polarity. If the data have polarity, usually they are very good quality data. But no, I mean, the quantity of information for quality is very limited.
Yeah.
The thing that absolutely doesn't work is the weight. When analysts put a weight on the data to estimate the quality, usually there is no information.
But they put weight themselves when they do manual review, or they use the uncertainty?
Now, when they do pick manually,
They do weighting, or they are identifying uncertainty of the peak?
weighting.
Wow.
Yeah.
Okay, that's not common here, okay. But
It's
that's fine, and I have one last question.
Yeah.
You talk about side effects, you haven't explained that a lot. But when you talk about side effects, you talk about the time residuals of averaging the time residuals of each station?
yeah,
That is what you
basically,
did?
yeah,
Okay.
yeah.
Okay.
We call it that because it probably corresponds to the area around the station where all the rays crossing this area gets to this station.
Yeah.
It's like close to the surface, so it's kind of an average of what's happening just below the station.
Yeah, it's more like a geometrical sprinting part.
Yeah,
Close
yeah.
to the station, yeah. Thank you.
No, you're welcome.
All right, cool.